Okay, so the reason we're leading up to all the things are going to kind of come together now. So we talked about Lewis structures. We talked about shapes, most importantly. We talked about polarity of bonds. What we're going to talk about now is, so I just talked about the sort of polarity between two individual atoms. Now we're going to look at the polarity of the whole molecule. So now we're going to throw in more than just two atoms. I'm going to look at the entire molecule. So we can classify a molecule on the aggregate as polar or nonpolar, sort of like a bond, right? So a polar molecule is where you have the centers of partial negative and partial positive charge are not the same. Another way to say it is where you have one end or one side of the molecule has a charge. So just like we defined this bond as being polar because there's a negative end and a positive end, you can have a whole molecule that has a positive end or a negative end, and a negative end. If it has a positive end, it must have a negative end. So here's how we figure it out. If the molecule has polar bonds and they're asymmetrically distributed, so this is kind of hard to describe, but let's look at a couple examples first, and then I'll try to go to some generalities. So I'm going to look at two nice, easy examples first. Let's look at HCN and CO2. Now, I actually want you to take a minute, and I want you to pause it and draw the Lewis structures for both of these. We've probably drawn them before, but try it now. And also, I want you to predict the shape, the molecular geometry. Because molecular geometry is critical to understanding this. You can't, if at this moment, a little bit of a caveat, if at this moment you don't understand how to determine the shape of a molecule, go back and study that and look at the video now, because there's no point in going on if you can't figure out the shape, because it's necessary to do this. So, go ahead and pause it. All right, so the Lewis structure you should have gotten would look like this, right? And for this, it'd be CO like this. This is what you should have gotten. All right, now, what shape? Both of these are going to have the same shape. They're both linear. So I've drawn them both already linear, right? So it's two electron groups around the central atom. They're linear. Okay, there's a difference here. So look, remember I said that H and C are they're nonpolar, so there's no real difference here. But here between C and N, right, there's this draw. We've got a negative end and a positive part of the molecule, right? We have an end. They're asymmetrically distributed. It doesn't have to be the charge is all the way on one end of the molecule, but there's different parts of the molecule have different charges, right? Let's contrast that by looking down here. Carbon has sort of one polar bond going towards oxygen. Oxygen, being further to the right on the periodic table, is more electronegative than carbon. This other oxygen is going to have something like this, right? So what happens here is, yes, there is a negative here and a negative here, but actually that's not really what happens, because if you think about this whole molecule, the electrons are sort of connected across the whole thing. These two oxygens are sort of just tugging against each other in exactly opposite directions. So you can think about it. My analogy, my silly little analogy, and this is the best one I've come up with so far. Imagine you have two people. I'm trying to think of how to best describe this. Imagine you have ropes. You can either think of people pushing or pulling on a ball. So imagine you have two ropes and they're both pulling against this. And they're both pulling with equal force. Does the ball go anywhere? The answer is no. The ball doesn't go anywhere because they're pulling with exactly equal force. Because these are both the same atom, right? they end up pulling with equal force. So you get a non-polar molecule. So there's no, though there are polar bonds, they are exactly evenly distributed. So this molecule ends up being non-polar. This molecule, HCN, ends up being polar. Right? Okay. We got to take a few other things. We got to look at a few other things. Okay. We got to start hashing this out a little bit more. All right. So that one's kind of easy. Let's take a look at these other molecules here. So I'm going to do a modification on HCN. I'm going to take FCN. Okay. Here's the thing. Now, if we look at this, it's still linear, right? Nitrogen is still more electronegative than carbon. And actually, I'm going to draw this arrow like this. Right? But fluorine is more electronegative than carbon. But the difference is fluorine is a lot more electronegative than carbon. The difference between fluorine and carbon is greater than the difference between carbon and nitrogen. So what ends up happening is there's this overall net electronegativity, this overall net polarity towards the fluorine. Right? They don't cancel each other out because they're not the same strength. If you have a ball and you have like a big adult pulling on it this way and a child pulling on it this way, the ball still slowly moves. Does that make sense? The child may slow down the adult pulling on it, but it's not going to stop it. Right? So in order for a molecule to be non-polar, all of the arrows have to exactly cancel. They have to be exactly the same magnitude and strength and all that. This is probably a very small number of you. Any of you who have ever done vector math in a physics or an algebra or a physics or a math class, this actually is much simpler for you probably, because what I'll say is the vectors of the bond polarities, if they cancel out to 0, then it's non-polar. If they don't cancel out to 0, it's polar. Okay, a couple other weird little examples we have to look at. All right, so now those were pretty straightforward. Let's look at water. Right? What's more electronegative, oxygen or hydrogen? Hopefully you said it was oxygen. Right? So, I'm going in like this. So this looks like it's going to be nonpolar, right? Well, there's something we didn't take into account. Water is definitely polar, and there's something we didn't take into account, and that is the actual shape of the molecule. I can't just start doing this ham-fistedly on any Lewis structure. I have to take the actual shape into account. Water is bent. That's what water looks like. So when we now have the two, imagine I have a ball, and I have two people pushing this way and this way, right? The left and right portions of their motion cancel out to 0, but they're both still pushing this way, up, so there's a net movement that direction. So they partially cancel each other out, but not completely. So the net is there's a negative here and a positive on the hydrogens. There's a net movement that direction. So the shape is critical. Okay, so let's do a few more examples. Let's do COH. Let's do this. Okay, which is more electronegative, carbon or hydrogen? Hopefully you said carbon a little bit, but they're considered not polar. But oxygen is more electronegative than carbon, so what we have is we have a net movement that way. Right? We also have to take that shape into account. It's trigonal planar. Right? Okay, two more examples. CF4 and NF3. When you do the Lewis structures, you get this. NF. By the way, don't try to do the Lewis structures the way I'm drawing. I already know what they look like, so that's why I'm able to just do everything kind of in this order. You need to do it by that systematic methodology. So we can look at these. Now, in both cases, fluorine is going to be more electronegative than carbon or nitrogen, right? The shape. We have to take the shape into account. We get different answers because of the shape. Carbon is tetrahedral, right? Now, nitrogen has a tetrahedral electron geometry, but its shape is different, right? Its shape is different. Nitrogen, so if we look at carbon, right? All these fluorines, it may not look like it, but they're all exactly 109 degrees from each other. They're all evenly spaced out. They all cancel each other out directly, exactly. They all completely cancel each other out. So this molecule is non-polar. This one, if you contrast it with CF4, this tells you that in order for them all to cancel each other out, you have to have one here, one here, one here, and one here. You calculate the necessary components to charge. They are. When you see a lone pair on a central atom, it's very probable that that molecule will be polar because that represents a blank spot in that even distribution where an atom would need to be in order to cancel it out and make it nonpolar. So, this is going to be polar. Another thing I should show you is everything has to be exactly symmetrical. If I replaced any one of these with, say, bromine, it's now polar. The molecule is now polar because the bromine isn't pulling as strongly. It's like the child again trying to help, and they overpower it, right? The other three fluorines overpower it, and the net charge kind of going that way and kind of back away. So really, here are the kind of guidelines. And I'm not sure which of these are going to help you more. So I'm going to talk about the guidelines that make something, kind of the general things you'll see that make something polar, and the general things you'll see that make something non-polar. So typically, oh, sorry, there's one last one I have to cover. Ozone looks like this. Do you think this is polar or non-polar? So its shape is bent. Hopefully you said non-polar. It's non-polar. Yes, it does have a shape that is bent. It has the lone pair up here. However, the problem is these bonds aren't polar to begin with, right? They're non-polar to begin with. So you have no polarity to start with, right? So there's no arrows to draw. It's non-polar because they all have the same electronegativity, right? Oxygen, 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 all have the same electronegativity. Anytime you see carbons and hydrogens, they're going to be non-polar because there's not enough difference in their electronegativities to be considered polar. Now, I'll say this, and that's if you have only carbons and hydrogens. Okay, so anytime you have only carbons and only hydrogens in a molecule, it's going to be nonpolar. There are other element combinations that give you that, that are close enough in polarity, they'd be nonpolar. I don't expect you to know any of those. The only one I expect you to know is that carbon and hydrogen together are nonpolar. Okay, so here's my general guidelines. Okay, a bond is polar, or a molecule is polar if the molecule contains polar bonds. That's why ozone fails. It doesn't have polar bonds to begin with. And the partial charge is asymmetrically distributed. A molecule is nonpolar if it contains no polar bonds, like ozone, or contains polar bonds, but the charge is distributed evenly, symmetrically. So, here are sort of the guidelines. Here are the things you're going to see. Polar molecules are going to tend to be Actually, I think it's easier to define what's nonpolar. A molecule will only be nonpolar, let me rewrite that legibly, if, one, it has no polar bonds to begin with. At all. No polar bonds at all in it. And that could be because the two elements are the same, or because it's all carbon and hydrogen, whatever. Or if it has polar bonds, and it's perfectly symmetrical. Right? It's perfectly symmetrical, meaning the only shapes that are going to allow it to be symmetrical are linear, trigonal, planar, and tetrahedral. What do all of those shapes have in common? They all don't have lone pairs on the central atom. That's what they have in common. So, because lone pairs on the central atom kind of mess up the whole works. So, they have to be one of these shapes and all the same element around the central. There's a lot of criteria here. So, for example, it's like I was showing you, if I had carbon, this fluorine, 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 bromine, right? Yes, it is tetrahedral, but they're not all the same atom. It has to be exactly the same all the way around. And this is one way you can think of it. A molecule has to either have all nonpolar bonds, or it has to be exactly the same all the way around. And you can think of it this way. A lone pair is the same as having a different atom. A lone pair screws up the symmetry. So, same, same, same. Oh, lone pair, screwed up. So can't have that. So now it's polar. So it's hard to set down just a set of rules. I think it's easier if you can go. It's harder to do, but it's more reliable if you can draw the shape, look at where the polar bonds are pulling the electrons, and look at the overall direction of the polarity. Drawing the shape, as I said, is critical. You can't analyze these things without looking at the shape.